Hello and welcome back to Calculus 1 section 4.3 on first and second derivative test, also known as what derivative tells us. So here's in one picture on what we get to discover and talk about in this section. If you have some function f of x, we already know how to use limits to come up with asymptotes and end behavior. So those are pre-calculus concepts which we use the limit for to kind of make it concrete. So tonight, what we are going to talk about is, well, a couple of things. First of all, we know the maximum here will be here, let's say, at x1, and the minimum here at x2. So we have a max at x1 f of x1, and we have the minimum at x2 f of x2. This is what we did the last class. We know that we are supposed to set the derivative equal to 0 and then go from there. Now, what we are discovering tonight is this. This part of the function is when the function is increasing. And also this part of the function here is when the function is increasing. And then we have this part of the function here, which is decreasing. So we are going to use the first derivative test to find the intervals of increase and decrease. Now, another concept that we are going to consider is with the second derivative test. Let's go. Let's find something less neurotic. Here. We are going to consider this part here. And that will be concave down, meaning spills the water and has the, right, it can't hold the water because it's open downwards. And then there will be another one on the other side, gray or orange. Then we're going to have right here orange going all the way up there, and that one is going to be concave up. There we go. All right, so you have a whole bunch of these colors on the pile, and I hope that you can follow the color coding, right? We have, I forgot to put in a value, call it x3. Okay, cool. So what am I going to say over here? From negative infinity to x1 union x2 to positive infinity, f of x is increasing. Why is it increasing? Because as you walk on the line and move to the right, you are going uphill, increasing. Then we have the green part between x1 and x2, and that's f of x is decreasing. Decreasing, i.e. walking down. Note that I am not using any y values. These are all intervals on x. So from one value on x to another value on x, you have the function increasing, i.e. going up. And then, so if you go from negative infinity on x to x1, function is increasing. And then after x2 to infinity, function is also increasing. Then the green decreases. Then we go, and maybe I can put the colors as well. So now we also have negative infinity to x3, and that's when f of x is concave down, and concave down means looks like that. And then from x3 to positive infinity, f of x is concave up, meaning looks like that. So concave up holds the water, concave down spills the water. I think if you're thinking about a cup. So this was our orange. Then I have the pink, and I have the green, and then I have the blue. And everything is now color-coded to fit this graph. So when you have the function, you can talk about increase and decrease and concave up and concave down. Now, I hope that you see immediately that you get min and max for free when you do these calculations to find where the x values, right, which parts between which two x's, right, the function goes up or down. You see that x1, the function rises, and then it falls after it, which means it's a maximum. Also, if you have the concavity levels, concave down must have a maximum and concave up must have a minimum. So once you find locations where min and max occur, by looking at the first or second derivative, it doesn't really matter. Whatever derivative test you want to look at, it will immediately for free tell you what are the which critical points are minimum and which critical points are maximum. Let's take a look at the first derivative test theorem. And we'll call this FDT, first derivative test. And it's very simple. It's the same what we talked about, I believe, on a second lecture of chapter 3 or whatever, when we connected the graphs together. We said if f prime of c is less than 0 on some interval a, b, where c is in between a and b, right? So if f prime is it, then f prime of x is decreasing let's just go to next line, is decreasing on AB. Next statement, if f prime of c is larger than 0 on some interval AB, then f prime of x is, oh, holy nightmare, not prime, original function. If the derivative is less than 0, original function decreases. If the derivative is larger than 0, the original function increases. So is increasing on AB. if f prime of c equals to 0, then you have a critical point. Or inflection point. We'll define that soon. So if f prime of c equals to 0, then x equals c is min, max, or inflection, and we're going to deal with that. Cool. So this is the first derivative test, and yes, you get to put this on a cloud. An exam question might ask, state the first derivative test. You write this from the cloud. If the first derivative is decreasing, is less than 0, function is decreasing. If the first derivative is more than 0, the function is increasing. And if f prime is equal to 0, then x equals c is the minimum, maximum, or inflection. So now we can work out an example of this and test the parts. So let's x cubed minus x. Hope that works. So f of x equals x cubed minus x. What happened? So in order for us to do the first derivative test, we first have to get the first derivative. So f prime of x is equal to 3x minus 1. 3x squared. Yeah, please pay attention. Yeah, thank you. 3x squared. So we have 3x squared minus 1. And we are going to set that equal to 0. We are going to get 3x squared equals to 1. X squared equals to 1/3. And finally get x equals plus minus square root of, well, let's go just square root of 3 over 3. When you rationalize, that's what you get. Square root of 3 over 3. This means I have two critical points, and for the procedure on how to do the first derivative test, we partition the domain at critical numbers.
So negative root 3 over 3 and positive root 3 over 3.
So we just draw the number line from negative infinity to positive infinity with these two barriers, negative root 3 over 3 and positive root 3 over 3. So there's an I missing over there. I can't. Maybe blended with the O. So the partitioning, right, is happening at critical numbers. We're also going to learn that it happens at the vertical asymptotes, but we don't have any in this case, so it doesn't help us. So we partition the domain at critical numbers, and then pick test points, because, well, that's in each interval. So that's your procedure. You are going to pick 0 in the middle as a test point. You can pick, let's say, -2 and +2, -100 and +100, or -100 and +2 million, whatever. Right? You will be picking the values in every region. We have 3 regions, from negative infinity to negative root 3 over 3. Then we have from negative root 3 over 3 to positive root 3 over 3. And the third region from root 3 over 3 to infinity. So I have 3 regions. I have to pick a test point, and those are your C's. Those are the ones you are testing and looking for the derivative to be smaller or larger than 0. So, to do the first derivative test, I have f prime of negative 2. Now, I know my f prime is 3x squared minus 1. So, 3x squared minus 1, which is 11. That's larger than 0, implying that f of x is increasing, which is why I am going to draw this arrow going up in the first region. So you have to memorize the statement, guys, in the cloud. You have to memorize the statement in the cloud, because once you do your partitions using the critical numbers, you know how to find critical numbers. You set derivative equal to 0, those numbers pop up. When you do the partitioning, you will have a number of partitions. Maybe 2, maybe 16, I don't know. Each one of those partitions, you pick a number somewhere inside, and each one of those numbers is the C. So you will plug that in the derivative, and it will give you the value either larger or smaller than 0. So my first test point gave me larger value. Now, f prime of 0, which is the second test point, which is 3 squared minus 1, which is negative 1 less than 0, means that the function decreases on this interval. And f prime of 2 is 3 times 2 squared minus 1, which is also 11, larger than 0, and f of x is increasing. Now, blue. For free. What do we see for free? What's happening within min and max? Where's my min? Where's my max? Yes. So, max at x equals negative root 3 over 3, because you can see that the function goes up, and then when it reaches negative root 3 over 3, it's going to fall down. I can calculate the y value, right, by placing negative root 3 over 3 into the original problem and figure out what the y is. But at least I know there is a max at that. And then I also know that there is a min at x equals positive root 3 over 3, because the function, as you can see, dips down and then bounces up when it hits the minimum at root 3 over 3, x equals root 3 over 3. Again, these points do not have y values yet. You can find the y values and list them as points, not just x equals. But for us, it's enough to just know that it's at x equals, because you can always calculate the y component, y coordinate, because you have the function. So that should not be an issue. All right, now what is the answer for your grade, right? The final 2 points is when you present the reader with the intervals. So you will start that from negative infinity to negative root 3 over 2. Negative root 3 over 3. Union root 3 over 3 to infinity. F of x is increasing. And then negative root 3 over 3, comma, root 3 over 3, f of x is decreasing. This is what you provide for the full credit, right, answer. Everything above this is calculation. But what you have in a box are the intervals on which the function is increasing and function is decreasing. You want, in some cases, increasing functions, in other cases, decreasing functions, right? Depends on the applied case, right? If it's money, obviously you want increasing function. But you know that the stock prices, right, they fluctuate, go up and down, up and down, up and down. Those graphs look like the EKG of the heart attack every time you look at them. That's probably why they are like that. So let's pick up. Let's go with another example immediately. Another example of f of x equals 3 over x. F of x equals 3 over x. You know the drill. Your job is to set the derivative equal to 0. If you get nothing from it, well, such is life. And your partitioning is going to be done through vertical asymptotes in this case. So, problem might have min and max values and vertical asymptotes. You will use all of them to partition, okay? So, when you do the first derivative test, you will partition your domain using all critical points and all vertical asymptote locations. In this case, we don't have any critical points, but we do have a vertical asymptote at 0. So you will have two partitions, right? There will be a partition at 0, right? A 0 dividing line, and there will be partition negative infinity to 0 and 0 to infinity. So f prime of x is negative 3 over x squared. When you set that equal to 0, you get negative 3 equal to 0, which is not true. There is no critical points, which implies no min or max. All right, sad face. Now we know for this that there is a vertical asymptote at x equals 0. So now in blood over here, we also partition over vertical asymptotes. So my first derivative test over here is going to be draw the domain from negative infinity to positive infinity, and then draw this wall at 0, and now you have two partitions, one to the left, one to the right. So now we'll pick test points, which clearly should be negative 1 and positive 1, because those are cheap values and they are available. I mean, can you use e to the pi? Of course you can use e to the pi. Exactly, right. So I drew my domain and then the partition, and now I have the test points. So now I do the first derivative test. F prime at negative 1. Well, that's negative 3 divided by negative 1 squared. And that's going to be negative 3, which is less than 0. So we have the function decreasing, right? So we draw a decrease in that part. Then we have f prime of 1, which is negative 3 no coughing over 1 squared, which is also negative 3. And we see another decrease. There is no change in increase-decrease, which means there is no min and max at all. And this is also an awesome example because you see that you don't get to alternate always up and down and up and down and up and down. Right? You have, or increase, decrease, increase, decrease. You have two that are going down. So no min, no max. And your answer is, you can start with f of x is decreasing on, and we have negative infinity to 0, union 0 to infinity, which is the entire domain.
Could you just put negative infinity to infinity? Oh, because of 0.
0 is the vertical asymptote.
Yeah.
In the next section on Thursday, we are going to add a graph on top of this calculation. Same calculation on Thursday. We're just going to do the graph in addition to what we do here. So this is your answer. You have no min, no max in this one. What was that? You want a trick question? Sure. So, f of x equals sine 2x. You don't want 2x? Okay, fine, 3x. I heard. To the 10th power, yes. I mean, it's not impossible. Yeah.
Oh, you play soccer now?
Or, and then I use hands when I have to.
Yeah. Part 1 is on Showbox.
I watched the original one. It's 9, read the book in 93.
I've watched the original one. I never saw it.
Yeah. The book was scarier than the movie.
I've heard
Much scarier than the movie. And they did the most fun which is rare.
Yeah, because they split it. You're going to derivative at
No, they did say it in the action.
No, was it? Oh, okay, so when I watch a movie now, it's just one long 3-ass hour movie.
Now it's
The
four.
sign of x.
Yeah.
4 and 5 hours.
Yeah.
They got more stuff.
I think the first part.
They got the fun. They got the fun.
Yeah. I had no idea about that first scene. You know,
Derivative of sine x will just be sine 3x plus 3x.
Georgia.
And then times 3 because the 3x.
I was not expecting that.
So it's 3 cosine. Right? Yeah, 3 cosine x. Yeah, 3 cosine x. Yeah, no, I'm sorry, 3 cosine 3x. You were right about that. I'm sorry.
Yeah, he was that bike shop. Were they making fun of him for saying that he could never write the engine for that? Because they kept bringing that up. You know, like, oh, you shouldn't be an engine for the entire time. And then even Stephen King said, they made fun of him for the first movie's ending because it was Simpsons. You don't think so? I thought they were doing
But we have to do it in like 5.
Yes, with ends, there will be infinitely many intervals of increase and infinitely many intervals of decrease.
Oh, because it's
So you will be using n in your final notation. Yes, very good, very good, very good.
yeah.
Huh?
Proud teacher.
All right, let's talk. Should have one of those moments from the office when balloons should never touch the ground. All right, let's go and take a look at this wonderful example by obviously popular demand. You all wanted a trig example, so here we have a trig example. Now, obviously, this would be an introductory trig example. It's not like it has a tangent squared times secant or something. All right, so we start with the first derivative, f prime of x, which would be 3 cosine 3x, and then we are going to set that equal to 0. The 3 in front would die when you divide, and you have cosine 3x equals 0. Now, when you draw a cosine function, you know that the cosine function hits 0 at pi over 2, 3 pi over 2, 5 pi over 2, right? So your cosine hits the 0 every time when you have what? Right? Which one? Yeah, but not every pi over 2, because pi over 2 and then the next pi over 2 is actually a pi. So it's every other. So it's every odd pi over 2, right? So 2n minus 1 for odd numbers and then pi over 2. But now that needs to be 3x equals that. 3x equals that. So now you divide by 3 and you get your x values for partitioning, which are 2n minus 1 pi over 6. Very good. There we go. Awesome. So now we have all of these for all of our partitions, infinitely many of them. So we're just going to do few partitions, because we all know that this is a wave that will go up and down, up and down, up and down. So we know they will alternate. So what am I going to do here? Well, let's pick the first one to be for n equals 0. If n is equal to 0, we have negative pi over 6. And then for n equals to 1, we have pi over 6. And when n is equal to 2, n equals to 2, that's 4 minus 1 is 3 pi over 6. Now 3 pi over 6 is actually pi over 2. And this is going to go forever in both directions the same. Your job now is to pick the test values. And the reason why I like to keep the same denominator, I know that this is pi over 2, but I'm not going to use pi over 2. And the reason is it's much easier to deal with the test points. You see, the test points here are always in the middle. So there is a 0 test point on the first. And then between pi over 6 and 3 pi over 6, there is a 2 pi over 6 in between, which is pi over 3. So if you keep denominators the same, it's very easy to pick in between numbers because you just look at the numerator, right? So it would be a living nightmare for us to pick between pi over 6 and pi over 2, right? But when I have pi over 6 and 3 pi over 6, well, clearly 2 pi over 6 is in between. So if you are keeping your denominators all the same across for trig, you will always be able to easily pick the middle value. Relatively speaking, right? We can use other words like obviously and simply and can do the proof by intimidation. Right. From where it simply leads to, and then you go simply work it out. It's like 30 minutes, it's like 6 pages of work. Oh, simply works out? Great. All right, f prime at 0. We are testing now. This is the first derivative test, right? When you do the partition, and you are looking for whether it's going to be increasing or decreasing. So f prime of 0, you will plug this into your 3 cosine of 3 times 0, which is 3 times cosine of 0, which is 3, because cosine of 0 is 1, right? And that's larger than 0, so f of x is increasing, so we'll draw the arrow up for increase. The next value we are testing, f prime of 0, is, this is pi over 3. So 3 cosine of 3 times pi over 3. Now these puppies cancel, and you have 3 cosine of pi.
So that's f prime of pi over 3 then, not...
Oh, yes. Pi over 3, yes, thank you. Which is our second test point. We get negative 3, which is less than 0. So now f of x is decreasing, and that's this. Now we know the next one is increasing, and then it's going to be decreasing, because it's a trig function. So it goes up and down, up and down, up and down, up and down. So the only thing that is left to us is to write an answer, right? Write an answer giving all intervals for decrease and all intervals for increase. Well, that shouldn't be too terrible, hopefully. What should we do? So we see that the increments are at pi over 3. Do we all see the pi over 3 increments? From negative pi over 6 to positive pi over 6, there is a pi over 3 of an increment, right? And then there is another pi over 3 and another pi over 3. So every other pi over 3 interval is the increasing, and all of the other ones are decreasing. So I just have to figure out, and this is what, you know, computer science geeks all love this stuff, because you have to figure out how to write these repeating sequences. So would anyone like to suggest the answer?
I'll try it.
Sure.
Union, it would be negative pi over 6 plus pi over 3n. No. Not everyone.
That was perfect. So negative pi over 6 plus, and the increments are for every pi over 6, right? It needs to go from this pi over 6 to this one over here to give us, so the first one that we are considering is pi over 6. The next one is 3 pi over 6. So we are going to add the increments and then use the n to denote that we can go down the line.
Pi over 3? No.
Well, to find, you can simply figure out the distance between these guys, which is 4 pi over 6, right? The period difference between these two is 4 pi over 6, which is 3 pi over 2. I mean 2 pi over 3. The period distance, right, the period is 4 pi over 6, which is 2 pi over 3. And that's what you put the n as well. So plus the period of 2n pi over 3. So that's the first value, comma, pi over 6 plus the same 2n pi over 3. F of x is increasing. And then you start at pi over 6 plus 2n pi over 3, comma, 3 pi over 6, that's pi over 2. I'll have to use the simplified version here. So pi over 2 plus 2n pi over 3. And that's where f of x is decreasing. And that is the answer. Oh, I did not write, oops, I did not write what n is. N is 0, plus minus 1, plus minus 2, plus minus 3, meaning that n can be any integer, any whole number, anywhere. So this is one of the straightforward trig examples because it was assigned. Yes?
Scroll back up to the graph.
Oh, this is the graph for cosine. This is not the graph for this function.
Oh, okay.
This graph for cosine was only for us to see where cosine cuts through x-axis.
I'm sorry, I meant the one, yeah, that one. Yeah.
Oh, you meant this, yeah.
Yeah.
Goes up, goes down, goes up, goes down, goes up, goes down.
So that up thing, that's the derivative of the concave down.
Oops. We didn't talk about concavity yet. Concavity is the second derivative test. We are only worrying about increase, decrease, which is the first derivative test. Now, you can also say infinitely many max points at pi over 6 plus 2n pi. Right? That's free stuff. For free, x equals pi over 6 plus 2n pi over 3 max. Right? Pi over 6 was a max, right? Yep. And then pi over 2 plus 2n pi over 3 min. So those are free of charge. Now all of this gets to be way simpler if you are on the closed domain from 0 to 2 pi or 0 to pi, and you don't have to mess with these ends and periods, right, to find how far they repeat and all of that. So much easier problems as you go. Let's take a look at one more example. So we did polynomials. So let's find either exponential or logarithmic, something beautiful that you are going to enjoy. So something nice. Oh, beautiful. With the sound effect over there. Here we go. f of x equals square root of x times ln x. What is the domain of this function? 0 to infinity. Very good. And the 0 to infinity, is it including 0 or excluding 0?
Including.
Oh, you're going to take it outside now and then? Or you're going to make the mathematical argument?
Oh no, it can't be 0.
It can't be 0 because of the log. Very good. It cannot be 0 because of the log. So domain for this problem is 0 to positive infinity, excluding 0, so use parentheses on both ends. Good. You know the drill. Take the first derivative, set it equal to 0, get critical points. Now, if there are no partitions, then the whole problem is one partition. You get to pick one number, and that's it. It's a single calculation. Sure. I hope. Gives you something to do while we're
Hey Nick, so in this case I think it's taking a negative number, right? The values. You don't need a calculator. On that side, it's not equal to it. Over there, you see this is 1 over this, the 1 over this cube. 1 over e to the 10, 1 over e to the 12. Okay.
If you make the denominator bigger with the same numerator, make the denominator bigger, you make the factor smaller. Because more people are sharing the same cup.
Okay.
Right? That's why
Joker kills everyone at the beginning of the.
Don't even talk about the movie here.
No, not the Joker in Batman. I didn't see the new one yet.
They said that was cool.
I wait for all the girls to stop going first and then.
Definitely been watched.
Why? Why?
Because they're acting and crying and then. I want to watch a movie. Right?
Why they cry at Joker though?
I don't know, I heard so.
It was quite. It was quite.
I think they only cry at
It was depressing and violent.
We're supposed to
The thing is, it was not
Adam
bad
Sandler
as
is the
that
Joker in my
created
right
it.
mind.
It was toxic society that created it. And I really liked how relatable it
Maybe we should go after one of the
It
Tuesdays.
was so fucking plausible.
Oh, yeah.
And, like,
Down.
I haven't seen it.
society
It's good.
that created it.
I don't care.
Like, it
They
could
have
happen.
holy.
It's
Hillsborough or
it could happen.
Manville?
That's
What
that's
are
all.
they?
Which one is the food one? I don't know.
But it's so uncomfortable. I didn't like it.
What, Amanda?
The movie one. It'd be cool.
It's either, for me, it's either Manville or Hillsborough.
CNN, MSNBC, all the like.
Bridgewater, I don't want
Yeah, they did now.
It's just
Alright, so then just.
that's how I hated it. They start spreading.
I'm not talking about popcorn and stuff like that. I'm talking about the meal
You see the Rotten Tomatoes?
Oh, not bad.
60. You get like Rotten Tomatoes. You get like Joker had 60 on Rotten Tomatoes.
Well, if we go to the menu one, I have free food.
From the audience.
What do you mean?
I work at the McDonald's right now, so
Yeah.
bullshit.
No, it went up. It went up.
I haven't had McDonald's in 10 years.
Like, I don't understand what exactly makes it a bad movie. I couldn't tell you like anything about it. Like,
Whenever you eat
I can't say
McDonald's
for
for 3 years, every day,
but it was like
live.
it was a movie that like stood on its own.
Not even
I
a
feel like a lot of
cheeseburger.
people wanted to stay through the narrative, like not whether it was expectations. There's a whole outlet of like, oh, it's gonna be
The new meat is good.
right, or it's gonna like.
Alright, let's take a look. I think most of the people are done because there's a lot of chatter, which is good. That means that the math aspect is over. Let's take a look at the derivative. What kind of derivative do I have? Product rule, very good. Copy the first derivative of the second plus copy the second derivative of the first. All right, now we are going to write this as square root of x over x plus ln x over 2 root x. And we are going to set this equal to 0. We know the domain is 0 to infinity, so that's great. So we don't have to worry about dividing by 0 because 0 is not in the domain anyway. All right, so now when we solve this, the fastest way is to ship this one to the right side of the equation and then cross multiply to get 2x equals negative x ln x. And then when you divide both sides by x, because x can't be 0 because domain, right? You will get, we can divide by negative x. You will get that ln x is equal to negative 2. You e both sides to kill ln, and you get that x is equal to e to the negative 2, which you can write as 1 over e squared. You have two partitions, so first the derivative test, we have two partitions now. We are starting at the brick wall, which is 0, and then we go out, and then there is another partition at 1 over e squared, and we are then going to infinity. So I have two partitions to worry about. This one over here, we can just say 1 as a test point. That's easy. Now, the one in here is trickier. Yes, you can go figure out what the decimal value for this is and then use the smaller number than that. But there is also a really cool way in using 1 over e cubed, let's say, because e cubed is bigger than e squared, which would make the fraction smaller, right? The larger the denominator, the more division happens, right? And smaller the pieces. So the larger the denominator, the smaller fraction. Great. So now we're going to do the first derivative test with 1 over e cubed. And for the first derivative test, I have this function up there, which is root x over x. So root x over x plus, and now I have ln x over 2 root x. Ln, really? Ln x over 2 square root of x. Great. Unfortunately, I have to compute this. And why do I say unfortunately? Because of ln, which is going to end up being negative. So I need to know the rest. Sometimes if everything works out to be negative, you know it's going to be negative. You don't need to compute all the way to the end. Just know what the signs are, and that's good enough. But in this case, we actually have to compute. So, what do I have? For the first one, right, I have this e go up, this one go down. So it's going to be e cubed divided by e cubed square root. Okay. So multiply 2 that are close by, multiply 2 that are far apart, all that good stuff. Now we have a plus. E to the negative 3, so it's just going to work out to be negative 3 divided by 2, and then root e cubed will go up because it was in denominator. Okay, great. So now I will multiply. Do I want to find common denominator, or I just need to know if this all adds to more or less than a 0. So I just want to know whether it's positive or negative. So what do I have? I have e cubed divided by e to the 3 halves, and I'll combine those exponents, minus 3 halves e to the 3 halves. And now, when I combine these exponents, that's going to be e to the 3 halves minus 3 halves e to the 3 halves, which is negative 1/2 e to the 3 halves, which means that we have less than 0, and the function will be decreasing. If you didn't follow the calculation, you can watch the video again, or you can just use the calculator and just skip all of this. The next one is f prime of 0, which is the second test point. No, lies, of 1. Not 0, 1. 1. And that's going to be, what do we have? Square root of x over x. So square root of 1 over 1 plus ln of 1 divided by 2 root 1. That's 1 plus big fat 0. Ln of 1 is 0. It's 1 larger than 0. The function f of x is increasing. Again, ln of 1 is 0. And because ln of 1 is 0, 0 divided by 2 is still 0. So that's what we have. and now this one is increasing, so here is the arrow going this way. What we got for free is that there is a minimum at 1 over e squared. So for free, minimum at x equals 1 over e squared. Again, if you want the y value, plug this into the original equation here in blood. If you want y value for the min-max point, plug the x coordinate into original equation. Right? So now what's our answer? Answer is the function is decreasing up to, okay? So answer, function f of x is decreasing on 0 to 1 over e squared. F of x is increasing on 1 over e squared to positive infinity. So this is what our answer looks like. You show the intervals over which you have increase or decrease. So that's the first derivative test. Your job is to find critical points, partition on critical points, and on vertical asymptotes. If there is nothing to partition, the entire domain is one partition. You pick one number in there, and then those numbers you pick are called test points. Those are your C's in the definition. And what you do is you are testing each one independently. I have that example up there that had, I believe, 3 values. There you go. So this problem had 3 partitions. We had 3 test points, and we tested each one individually to find. The good thing to remember here is do not automatically alternate, because you can have any combination of these arrows. It depends on what the function looks like. Do they alternate for polynomials? Yes. Fine. You win. Okay? Do they alternate for others? Not necessarily. And I did give you 3 over x. The next example, when you had a decrease followed by another decrease. So you are going to find alternating increase, decrease for sine and cosine and polynomials. The rest, hey, anything can happen. So that's the first part of the lecture. The second part is the second derivative test. Procedure is cut and paste. Same procedure, except on the second derivative. So what you do is you will find the second derivative, you will partition, and you will pick the test points, and you will plug them in the second derivative. It's called a second derivative test. What it gives us are intervals of concave up, concave down. Now, why would you care? Well, let's discover. So, second derivative test, SDT, you already know that what you're looking for, but before we actually do any of this stuff, let me ask you about money investments, all right? We are going to invest in the same time frame t, same amount of money in a different portfolio. The first portfolio will start at the 10K investment, go like this. Second portfolio will start at the 10K investment, go like that. And a third portfolio will start at the 10K investment and go like this. Which portfolio do you want to invest in?
That bottom one, bro.
Well, first off, let me ask you, which portfolio makes money? All of them. Thank you. That's what I want to know. Oops. All of these portfolios make money because the amount of money that you have after certain amount of days, years, months, whatever, is higher than your initial amount. So all three portfolios make money. Now my question is there any one of these that is better than others? And you guys said number 3. Number 3 is the best. Now why? Well, this one starts making money, right? The first one starts making money quickly, and then it kind of levels off. So the further in time you go, it will keep it at the level increase, right? Linear is always increasing, but look at the bottom one, right? So what we have here is concave down, no concavity, and concave up. So this is what we have, and this is what how they're different. This is why second derivative test is important. So we can't just claim, oh yeah, the function is increasing, good to go. Concavity measures the rate of change of increase. You can have a faster, slower, or steady increase, right? So you know that the derivative of the derivative is the second derivative, right? So if I'm talking about the rate of change of increase, I'm talking about the derivative of the derivative, which is the second derivative. So now we get to write our definition for the second derivative test, or theorem, or whatever. Number 1. If f double prime of c is less than 0 on some interval a to b, then f of x is concave down on AB. Concave down meaning downward opening. Number 2, if f double prime of c is larger than 0 on AB, then f of x is concave up on AB, and that's parabola opening up. Number 3, if f double prime of c is equal to 0, then x equals c is an inflection point of f of x. What is the meaning of the word inflection? Point the arrow at it and say change in concavity. Change in concavity. And we can add a sentence, we still partition over inflection points and vertical asymptotes. So now we'll just add a sentence, we partition over inflection points. So now inflection points are instead of critical points, okay? We don't care about critical points anymore. When you set first derivative equal to 0, you get critical points. When you set second derivative equal to 0, you get inflection points. And those are stronger, actually. So if you have your first derivative at 0, first derivative at 0 equals 0, and the second derivative of 0 equals 0, the second derivative wins. We'll see that. So we partition over inflection points and vertical asymptotes. So the first derivative and the second derivative procedures are identical. The only difference is which derivative you get to use. Let's take a look at the introductory example of x cubed. So if you are to take the first derivative, you will get 3x squared, and if you set this equal to 0, you will get 3x squared equal to 0, you get x equals 0. But the issue is that when you take the second derivative now, you get 6x, and when you set that equal to 0, you still get x equal to 0. So now the question is, well, which one is right? Do we have min and max? Or do we have inflection point? Well, if you know anything about the basic x cubed graph, do we have min and max? No, right? So this point here is called inflection point, and you get that inflection point from the second derivative, and you can see that this piece is concave down. You can complete that piece if you draw the second part on the other end. And you see that the other side is concave up, because if you are to finish it, it would be concave up and it will be holding the water, right? So these kind of squiggles, right, when you have these points, those are called inflection points. And they are change in concavity, because as you can see on the left over here, you have concave down. On the right, you have a concave up. So now for my x cubed, to just finish off this problem, since I have the inflection point at 0, I will partition at 0, choose the two test points at -1 and +1. Same procedure using the second derivative. F double prime at -1 is 6 times -1, which is -6, which is less than 0, which means that f of x is concave down. CD, concave down. F double prime at +1 is 6 times +1. It is 6, it's bigger than 0, which means concave up. Now, since our only critical point ended up being inflection point, we do not have additional critical points for min and max, so no min, no max. You want the full credit? Sure, right? I mean, if you don't want the full credit, don't worry about the answer. But for the final, right, 2 points for the problem, you will write on -∞ to 0, f of x is concave down. On 0 to +∞, f of x is concave up. Now, I already gave you an example where this is very useful. All of your portfolios make money The third portfolio on the bottom was the one making the money the fastest. And that was the one that was concave up. You are going to have these examples throughout your physics and your engineering courses and so on. So you should know concavity because it does show the rate of increase. So that was introductory example with the x cubed. Let's see if we can find something in a section for whether it's concavity or second derivative test. And also, I'm seeing some problems where they say technology, capital T, the blue T. You need to make sure that you are using technology in that problem because it's not going to be pretty. I'm sorry? Generally, software to either graph it or calculator to compute values because they're not going to a numerical method to solve the equation. Not every equation, guys, can be solved algebraically. We talked about it at one point in time where I said that x plus 3 equals to ln x cannot be solved algebraically. There's nothing you can do here. Because on one side you have polynomial, on the other side you have transcendental function. You can solve, let's say you have x squared plus 3x minus 1 equal to sine x. You can't solve this. There is no algebraic witchcraft that you know right now to solve these things. When you're done with Calc 2, you'll have some tools. They're not going to be pretty, but you will have tools to deal with this, right? Right now, your only bet is to say the left-hand side is ln x, graphs like this. The right-hand side is like that. They will never intersect. No solution. Over here, whatever the hell this graph says, some kind of parabola, right? And then you will have your sine x going forever. Oh, perfect. There is a solution here. There is a solution there. Whatever, right, numerical methods bring you. So when you see a technology, that the blue T, that means that you will probably either have to graph it to get your solutions, or you'll have to use the software to either integrate, differentiate, or do something with the problem. Well, not differentiate, you should be able to differentiate anything. All right, which problem should you like? Well, 63 looks pleasant enough. G of x or f of x or whatever the hell of x is ln of 3x squared plus 1. Can anyone tell me anything about the domain of this function? All real numbers. Very good. We know that for ln of x, we have domain 0 to infinity only, because you can only plug in positive numbers in ln to get the real values. But when you consider 3x squared plus 1, no matter what x you plug in, whether it's positive or negative or 0, the full parenthesis will always produce positive numbers. So your x is allowed to be anything. Now that's important to know before you start doing anything. So domain is from negative infinity to positive infinity. Awesome. G prime, that's the first derivative. We know that we are supposed to cut and paste denominator and then put 6x on top. And now we have second derivative, g prime of x. And that's going to be, you can use the, what's it called, logarithmic differentiation if you want to, or you can use the quotient rule. Let's go with the quotient rule. We can use logarithmic as well. So square this, and then we have 3x squared plus 1 times 6 minus 6x over, and then another 6x. What happened? All right, that's what I thought. So 3 times 6 is 18x squared plus 6 minus 36x squared divided by, we don't care because it will die when we set it equal to 0. So the second derivative of x is, we have 6 minus 18x squared divided by whatever. And why do I say whatever? Because when we set it equal to 0, the whole denominator completely cancels. And we have to deal with 6 minus 18x squared equal to 0. This means that 6 is equal to 18x squared. Finally, x squared is equal to 1/3. And here we have again our x's of plus minus root 3 over 3 when you rationalize, right? Because when you put the root over the whole thing, you get 1 over root 3, and you rationalize into root 3 over 3. Don't forget the plus minus when you square root both sides. Awesome. I have 2 inflection points. 2 inflection points, and those 2 are, again, a negative root 3 over 3 and positive root 3 over 3. My domain goes from negative infinity to positive infinity. I have 3 partitions. Cheap numbers are negative 1, 0, and positive 1. And now we have to do the second derivative computed at each one of these. So the second derivative, really? There we go. So the second, The second derivative computed at -1. So what do I have? I have 6 minus 18 -1 squared divided by something squared. Why don't I care about denominator? Because it's squared and it's always positive. What do I have in the numerator? I have 6 minus 18 times something, again, positive. So I have negative divided by positive. That's going to be smaller than 0. And I have concave down. Didn't calculate a thing. Right? Next one. When we use 0, we have 6 minus 0 divided by something positive. So this is a 6 divided by a positive number. So positive divided by a positive. It's positive. Good. Yeah, it doesn't matter what it is. Because it's squared. It will always be positive. So I have positive divided by a positive. That's going to be larger than 0. And I have a concave up. Finally, I have 1. So second derivative at 1, which is 6 minus 18 times 1, which is 18, divided by something squared. Again, I don't care. That's a negative divided by a positive, also less than 0, concave down. So, answer, right? So if you care about the full credit, write this. Otherwise, don't worry about it. Negative infinity. So f of x is concave down at negative infinity to negative root 3 over 3 union root 3 over 3 to positive infinity. F of x is concave up, not at, on, interval, on, and then we have negative root 3 over 3 and root 3 over 3. Yeah, it's definitely time to go when I keep switching these and it's still on. I think there's a lot of lag between the server and the... So it's not working. Might be the cloud. Saved offline error. Yeah, it's... The cloud is messing up. Come on, I just need to write 2 letters and then we're done. Just need to write on over here. Can I write on? No? Excellent. Got it. Done. All right. So guys, the procedures for both of these are exactly the same. Just have to be careful which derivative you're using and what do they represent at the end. We are going to use all of this and more on Thursday to graph functions by hand. On Thursday you will learn how to graph this ln function without aid of calculator or graphing software. So that's Thursday. See ya.
Quizzes start tomorrow. Everyone, quizzes start tomorrow. Quizzes start tomorrow.